Hey, John here. Let's talk about this today, all right? The 8-inch floppy disk, IBM Diskette 1, it says on here. Genuine, bona fide detail right there. Record length, 128 bytes, okay? Let's talk about how CP/M is configured to use the data on a floppy disk. In version 2.2, one of the big enhancements for CP/M from the 1.x series was that you could now configure it to deal with disks other than just the 8-inch floppy, okay? However, as we'll see, CP/M still likes to think of the world in terms of these 128-byte sectors on the original disk. To see how all this fits together and find out what we need to do to make everything work, let's go back and have a look-see at our favorite pal, the CP/M 2.2 Alteration Guide. Now, remember what happened with our select disk routine. This is supposed to return the address of something called the disk parameter header. Okay? Right here. It's a 16-byte area that's supposed to be returned in the HL register. We returned a 0 to indicate that we had an error. Last time we were playing around with, when we stubbed this in, we just simply said no matter what disk was selected, we set HL equal to 0, which means back to the CP/M operating system that the disk that it wants to select is illegal, invalid, non-existent, whatever word you want to stick in there. It is in error. So in order for us to actually have a disk and do some I/O and talk to what we hope will be the SD card at some point, we need to return the address of this disk parameter header in a HL register. Now, the disk parameter header is one of the items that is defined in this section 10 over here called disk parameter tables. All right. We have this header. And then later on, you're going to see we have this thing down here called the disk parameter block, okay? Which is right here, right? The DPB, all right? So if we talk about the DPB, we're talking about this thingy here. If we're talking about the DPH, we're talking about this thing up here, all right? So the way this works is the BIOS designer is supposed to fill these things in to define what I like to think of as the geometry of each one of the disks that the CP/M system can use. Now, right now, we only have one. So by definition, what happens is it says each disk drive has one disk parameter header, which contains information about the drive and a scratch pad area that the BDOS will use to store, temporary data and stuff like that, keep track of what it's doing. And it's formatted like this, okay? So here's what we got. We got this thing called XLT, and it's defined down here. 3 values that are set to 0. These 16 Bs down here means each one of these fields in here is a 16-bit value, all right? Each one of these is 2 bytes long, all right? XLT, 3 scratch pad values are these 3 zeros here. The XLT is the address of another data structure that we're not going to use. This thing is used on floppy disks to deal with this sector translation stuff. I mentioned this last time when I said we're going to translate one-to-one. We're not doing the translation. We're not going to provide any skew factors and interleaves and things like that to optimize the performance of a floppy disk. If you're using an SD card, it doesn't physically move. You don't have to worry about mechanical timing and stuff like that, which is what this really concerns. So we're not going to use it at all. And it says you can put the value 0 in here if you don't want to do any sector translation at all. All right. So we're going to put a 0 here and 0s over there. We're halfway done already. Woohoo! Okay. What's this? Dir buff. This is going to be the address of a 128-byte scratchpad area for the directory operations within the BDOS. It needs a buffer to hold a disk sector from time to time when it needs to access the disk directory when none of the other memory should be touched in the system. So we have to provide a special dedicated buffer and let the operating system know where it is so that it can use it when it wants to manipulate the directory on the floppy disk. DPB, that's going to be the address of a disk parameter block. That's the thing I showed you below. That's the other data table, the other block, this so-called disk parameter block. Now, the reason you store a pointer to that in here is because they want to allow you to have multiple physical disks. Each physical disk would have one of these disk parameter headers affiliated with it. And you could have more than one physical disk share this DPB object that we'll talk about in a minute if all those disks have the same geometry, like same number of tracks, same number of sectors, and so on. Okay? So it allows you to save some memory. It turns out the same thing's true about the directory buff. All the DPH addresses can use the same directory buff. Okay? So if you had 10 drives, all 10 would point to the same directory buffer. You can also share all the same DPBs, but if you got a 5-inch, like a 5 1/4-inch drive and an 8-inch drive and an SD card, each of those 3 physical disks would have completely different DPBs because all those disks work very differently, and the geometry of the actual disk itself is what goes in the DPB. All right. What's the CSV? The CSV is a scratchpad area for software check for changed disks. This needs to be different for each DPH. All right, so we have to create another buffer, another scratchpad area, and put its address in here. Now that turns out to be optional as well, as we'll see. The idea behind this is that in CP/M, unlike the IBM PC era machines, the floppy disks in an IBM PC have a signal that comes out of it that physically can inform the operating system if the disk door has ever been opened, if the disk is ever removed and put back in. The operating system knows. In CP/M, it doesn't have that luxury. So if you take a disk out of the drive and put a different one in, if CP/M does not know that that has taken place, you can end up in a situation where CP/M thinks that the directory on that floppy has, some space available somewhere. And it might actually decide to start storing data there. But if you swap the disks out, you got disk A and you got disk B. Well, if you pull A out and swap it with B, it'll write into disk B thinking it's writing onto disk A. And it can corrupt both of the floppies if that happens. Now, the idea is that this scratchpad area is used to hold things like checksums and stuff like that. So what happens is CP/M will strategically reread the directory every now and then and checksum all the bytes in there, what's in use, what are the names of the files, and all this other stuff to try and figure out if somebody snuck the disk out and replaced it with a different one, okay, so that it doesn't accidentally corrupt everything. Now, this is optional, and I'm not going to use it. The idea being that you don't need to do this on a hard drive, on a fixed disk. And if the disk is never removed, then you don't need to worry about that. And it takes time to do this, especially on a floppy, because it has to spin the head out, and it has to reread the whole thing, do the checksum, and then ask, is it okay? Is it okay? Is it okay? And it's doing this all the time, okay? I'm going to just set this to 0, as we'll see, to shut it off. And the rule will be, you can't pull out and swap out the SD card unless you reboot the retro board after you've done that, okay? At least in this first release, right? Our prototype release. Don't swap the SD card out. Now, what's ALV? ALV is another scratchpad area that the BDOS is going to use. And again, this is different for each DPH. What this is going to be used for is it will hold a mapping that the operating system will use to remember where the free space is on the floppy disk. Okay, what happens is when you first put a disk in, let's say I put a disk in and then I type like B:. If I have 2 disks in the system and I put in a new floppy in the drive B and I say B:, what it does is it reads in the entire directory and it builds this data structure that represents where everything is on the floppy disk. That's why it's very important that you don't switch the disk once it's done this, because it keeps this cached all in memory, and that's where this cache is. That's what this thing is for, okay? And as I said earlier, the CSV can be used for it to just kind of redo this and ask, did it change, did it change, did it change all the time? Okay. So that's what's going to go inside here. This means, what does it mean? We need to allocate this DPB thing and a directory buffer, and of course the ALV. We're going to zero the CSV and the XLT, and that's this whole thing. So let's look at this DPB thing now. By the way, this section is a discussion on how to deal with the math, if you can't figure it out on your own, of what it means to have several of these disk parameter headers in memory. So if you have several drives, if you have 16 drives, you would have 16 of these headers in here, okay? And then your select disk routine would need to look something like this. All right, this down here is the math of it saying if I have a table of these things and I select drive B, I need to return the address of this second entry in this table full of DPHs. So they go through and if I know the address of the first one and I want to select drive B, which is drive number 1, I have to add 16 times this number to the address that represents where this whole table of DPHs is, okay? So that's what this code does down here. It also has a check to ask, is the drive letter okay? We'll look more about this in a minute when we write our own. In our case, it's super simple. We have one and only one disk, at least right now that's true. So all we're really going to do is say, if they didn't select drive A, which is drive number 0, then we have an error, and we will return an error, right? Just like we do today. If you return with HL equals 0, that means there is no such disk. If the drive that the operating system wants to select is in fact drive A, we don't need to do any math or anything because we only have one DPH. We'll return the one and only one DPH, and we'll be off to the races. Okay, so this is the big leap we need to make today. So when we boot this up, the operating system will actually be able to interact with the with our disk. Okay, so after this, what do we need to do? We need to come down here. We need to create this thing. Now we got to think about this for a minute. This is the one that talks about SPT. How many sectors are there per track? All right. Well, our SD card doesn't even have tracks. So what are we supposed to do with this, right? And what the heck is a data allocation block shift factor, which is determined by the block allocation size? Well, what the heck is a block allocation size? What is the extent mask? What is the storage capacity? What are all these things, okay? So some of these we get to choose as a designer of our BIOS and our disk system, or more particularly in my case, the retro board, right? How many sectors do I want to put per track on my SD card? Right? And how, what else do we get to choose? We get to choose how big is our disk, okay? The DSM, DRM, how many directory entries are we going to put on our disk? It turns out we get to make choices of these things. How big of a directory do we want? How many file names do we want our disk to hold? How many sectors does our disk gonna have? We get to tell it all these things. CKS, the size of the directory check vector. So this goes along with the pointer that's in the header, right? The header has a pointer to the check vector scratch area, and this field here, the CKS, in the disk parameter block has the size of that data structure in it, okay? So we're going to set this to 0 because we don't have one. Off down here is the number of reserved tracks at the beginning of the logical disk. Now remember, we talked about this before. This is an image of, if we have an 8 megabyte disk image that's extracted, that we're going to store along with other things on our 16 gigabyte SD card, right? This thing is 2,000 to 1 bigger than we're going to use, right? So let's zoom in down here. A little teeny bit of partition 1 is going to have an 8 megabyte image that we're going to use as a, we're going to masquerade as a floppy disk and in terms of what CPM thinks, right? It turns out that the operating system is stored down here at the bottom of our disk image. Now, again, we talked about this before as well. In the alteration guide, somewhere in here, there was this big table that shows how an 8-inch floppy disk works by default right here. And it said, look, the very first 2 tracks, we'll talk about diskette organization, yada, yada, yada. It'll say in here that the first sector is used for your boot image, which we don't use. Then, because our entire boot up startup logic is in the flash ROM on a retro board. And then it says all the rest of the sectors. So there's this little boot cold start loader. Ours is in the flash. All the rest of the sectors on track number 0 are used to hold the CCP and part of the BDOS. And then on track 1 contains more of the BDOS and the BIOS, okay? And then starting on track number 2 and up to the rest of your entire disk, in terms of tracks, is where the directory starts and the data goes. And by that, we're talking about this yellow portion and then this orange portion in the drawing that I have here, right? Your data and the direct. So our operating system is going to sit down here, and our SD card has, remember, SD blocks in it. It doesn't have tracks. And we're going to see in a few minutes that I've decided to consider, to translate this, to make this look like a floppy disk in terms of what CPM thinks it is. I'm going to make each SD block play the role of a track on a CPM floppy disk, okay? Therefore, our operating system, it won't fit in 2 tracks. It's going to fit in 32 tracks, right? And hex, it's 0 through 20, or 0 through 1F. The block numbers on the SD card, 0 through 1F, and which will become the track numbers in CPM's perspective of this thing, will be reserved for our operating system. So if it's an 8-inch floppy, by default with the standard configuration, CPM reserves 2 tracks to hold the operating system stuff. Ours is non-standard. It is much bigger than a floppy disk, and it's going to use 32 tracks to be reserved for the operating system. What comes after that is the directory. We'll talk a little bit more about that as we go. And then after the directory, which is where it stores all the file names, and there are these tables in there that store the block numbers, and we'll see what those are. Not SD blocks, but what CPM refers to as an allocation block, which is totally different than the SD card blocks, or the CPM sectors, or the tracks, and all this other stuff. So we're going to start by building a table of terminology, and then fill in these numbers, and then translate them to the alteration guide, so that we can define what CPM thinks of as a single disk that holds 8 megabytes worth of data. So back to our disk parameter block structure here. What is the total number of sectors per track? Okay, well, CPM thinks that a sector, no matter what, always has 128 bytes in it. And because one of our SD blocks is going to be the equivalent of 1 CPM track, we're going to need to tell CPM that there are 4 sectors per track, so that 1 track represents 512 bytes. So that's going to be a 4. The BSH, BLM, and EXM all come from these tables down here, okay? The way this works is that the allocation block size, which is what this stands for, we get to choose what that is, okay? depending on what we choose to make our CPM allocation block size, I'll talk more about what that is in a minute, that will dictate the values that we need to put for the BSH and the BLM. All right. And I'm highlighting this row in particular because we're going to use this for our allocation block size. I'll discuss that more in a minute. But if we choose this, you just simply look it up. BSH is 4, BLM is 15. Down here, because again, we've chosen 2K, what they're saying here is the EXM value up here, right? You get the BSH, the BLM. We look those up in this table here. The EXM value, which goes here, the third one here, and it's going to be determined by the BLS, which I said we're going to use 2K. And then it says, look, if the DSM is less than 256, your EXM is going to be 1. If your DSM value is greater than 255, then your EXM value will be 0. Okay? So, what the heck is DSM? It's described down here. It's the maximum data block number supported by the drive, which is measured in BLS units. So, if we have an 8 megabyte drive, and the BLS units, which, bear with me, is still arbitrarily chosen to be that number right there, is going to be 4095, right? I mean, 8 meg divided by 2K is 4K. Now, it says that BLS times DSM plus 1 is the total number of bytes. I just did that in reverse, right? It says must, of course, be within the capacity of the disk. Thank you for pointing out the obvious. Not counting the reserved operating system tracks. Now, what about the DRM? What's that all about? Okay. Determines the total number of directory entries which can be stored on the drive. AL0, AL1 determine the reserved directory blocks. I come back down here. The DRM entry is 1 less than the total number of directory entries which can take on a 16-bit value. The values of AL0 and AL1, however, are determined by DRM. The two values can be used together to be considered a string of 16 bits as shown below, and they number them in a wonky sort of way. The short of it is you have 2 single-byte values. This is the most significant bit of this first byte. And this is the least significant bit of this first byte. They just number them in a weird way. Don't worry about it. And what you're supposed to do is put a 1 in each one of these bits, starting from the left. It should be all 1s followed by all 0s. And where it transitions from being all 1s to 0s represents how many of these allocation blocks, which we've decided is going to be this 2K number down here. There's 1, 2K, 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 and so on. There's 1 bit set here for each allocation block that we want to dedicate to the region of our disk to hold the directory of the disk. Okay? Now we get to choose how big the directory is, how many entries are there going to be in there, right? And it tells you down here, if your block size, your allocation block size is going to be 2K, then each allocation block that's dedicated to hold directory entries can hold 64 directory entries, because each entry is 32 bytes long. All right, it's as simple as that. So if I want to make my directory hold, I'm going to make it be 16K. I'm going to need 16K divided by 2K total allocation blocks, which of course is 8. So what I'm going to do is I'm going to have 8 1s here followed by 8 0s. All right, that's what all this stuff means. And as a result, I'm going to end up with the ability to have 8 times 64 directory entries total on this 8 megabyte disk. All right, so I'm going to have up to 512 directory entries on my disk. That could be 512 files, or that could be one file that has what we call 512 extents. All right? We'll talk more about the way the directory entries actually work later on, but the beauty is we have enough tools, and somebody provided some tools that run on Linux to allow us to format file systems and use them without actually really understanding how any of them work. However, you need to know enough about how they work in order to configure the BIOS to know how everything got formatted and where everything is, all right? So at a minimum, you need to pick these things strategically to make everything simple. And it turns out that a 2K byte block size, the allocation block size of 2K, matches beautifully with the simplest way to format the directory entries that go on this disk. If you choose a size that's bigger, things get more complicated, all right? And they're more complicated not because we have to do more work, and it's really actually not something that we have to tend to unless we actually want to go in there and diddle with the disk data ourselves in this 8 megabyte image that we stored on the SD card. We can't ignore it and let CPM deal with it entirely on its own. However, we have to be aware of what the settings are, so when we interact with the SD card, if we plug it into our Raspberry Pi and we say, here, put all these files on the SD card so that CPM can see them, we need to configure both the BIOS and that command line tool to tell it what our block sizes are and how many directory entries we're having and all that other stuff, so they both are using the same parts of the disk image to do the same things, okay? That's what this all really boils down to. Beyond that, I've noticed that if you choose 2K for this, then your disk image matches what most of the documentation says that you can find floating around the internet. That's why we choose 2K. CKS, remember, this is your size of the check area, and it says do this math to figure out how to allocate it. I'm not going to do it. I'm going to set it to 0. No records are checked, okay? Because our media is, for all intents and purposes, fixed. We're not going to be able to pull it out and put it back in while we're running. You pull it out, you're going to have to reboot it. You think about that. Rebooting solves a huge problem with the SD card. Remember, if you take that out and you put it back in, you got to go through the entire SD card initialization sequence again, okay? If you don't do that, then no one can read or write anything to that SD card. So it just so happens that that fact is going to protect us from corrupting our SD card. If you do take it out and put it back in, and nobody reinitializes the SD card, then the BIOS is going to get nothing but errors when it tries to do I/O. And as a result, it'll prevent the BIOS from corrupting it, even if we shut off all of our directory checking. All right? So for now, that's what we're going to do. Finally, the last field, off. I already mentioned that is going to be the offset of where the disk image starts. That's the number of reserved tracks. All right, yes, so a number of tracks which are skipped at the beginning of the physical disk. This value is automatically added whenever set track is called, and can be viewed as a mechanism for skipping reserved operating system tracks or for partitioning a large disk into smaller segmented sections, which is kind of neat. That might give us the ability to put more than one logical disk into our partition here. Sort of, but not really. It turns out that we need a number that can go much bigger than 16 bits in order to make that work. Okay? Especially if we want 16 of these things. We'll come back to that some other time. Keep it simple. We're going to have single disk, and our offset value will be set to hex 20, because that's how many tracks are reserved for our operating system down here. And then they get to the point where they tell you how big you need to reserve the memory for your ALV. They remind us that we have to have a unique one for each drive. We're not going to use a CSV. Our size is going to be 0, but we do have to have the ALV. So what do you do here? This is for the CSV. We don't care about that. Down here, it talks about the ALV. So how you calculate how many bytes do we need to reserve for the ALV? It's the maximum number of data blocks that's allowed for the disk, right? And it's computed as this. So you got to have the DSM over 8 plus 1. And I would argue this math is wrong. They're obviously rounding a value up, okay? I would have done DSM plus 7 in parentheses over 8. As written, this will round up too much. And then they point out down here the overwhelmingly obvious and welcome statement that it might be useful to examine the example C BIOS code to see how we set up the standard 8-inch single density drives. Okay, now I scrolled over that once before, and we'll look back at that again, especially when we try to figure out to make sense of that one line up here when they say that, you know, the DSM is supposed to not include the operating system tracks. All right, so let's go back to our skeletal C BIOS and look and see what they did down here. Here's their disk parameter headers. This is a pointer to their translation table. Ours is going to be 0. The 3 zeros that they reserve, their directory buffer, their DP block pointer for this disk. And you'll notice that all the disks use the same DP block because these headers, there's 4 of them in here. These 4 disks are all assumed to be the same geometry. So they're all going to use the same disk parameter block. All of them have a different check and allocation vector. Check 0, allocate 0. Check 1, allocate 1. Check 2, allocate 2. Check 3, allocate 3. Okay? Then here's their translation vector, which we don't have because we're not going to do an interleave. And you can sort of reverse engineer what this thing is doing. I'll leave that as a test to the viewer if you want to know more about it. Then you get down here to their disk parameter block. Now we know, based on what we've just read, what all their intentions are. So we can go back and double check these to make sure that they're these values that are calculated based on the number of allocation blocks on the disk, which I think is this guy right here, whether it makes sense, and whether they're counting these 2 reserved skipped tracks or not when they calculate this number, okay? So let's do some quick math. If the disk has 26 sectors per track, and each sector is 128 bytes, then the total disk is 128 times 26 times 77 total tracks, okay? So the disk holds this much, about 1/4 of a meg, all right, on a whole giant 8-inch floppy disk, 256 total bytes. So that's the whole disk, right? Now, how much blocks, how many sectors, I should ask, are there on the amount of disk without the reserved tracks, all right? Well, that'll be 128 times 26 times 77 minus 2, right? Like this. So that's going to be the number of bytes on the 8-inch floppy, not including the 2 reserved tracks. So we need to reverse engineer using the block shift factor, the block mask, these values to figure out what their allocation block size is supposed to be. So what do we got here then? We got a block shift factor of 3, the block mask of 7. If we look back at the tables up here, the only entries in here that allow a 3 and a 7 is this one up here. Therefore, the block size, the allocation block size, must be 1K. Now, if the allocation block size is 1K, and the largest allocation block number on the disk is this, so it's really 243 total allocation blocks times the size of the allocation block equals this number right here, okay? That is the total bytes that comprise all of the allocation blocks that the disk has that we can use. Now notice this number here does not match either the total bytes, nor does it actually equal the total bytes not including the reserved tracks. Notice it's a little bit less than this value here. Total bytes not including the reserved tracks. Now the reason for that is because the 26 sectors per track times 75 tracks does not contain an integral number of round 1K values. So you have to round it down, okay? Because if we decided to say 244 times 1024, we do this math here, that number there is bigger than the total disk available bytes, not including the 2 reserved tracks. So you have to round it down. The last few sectors on an 8-inch floppy disk are never used. So the takeaway is that this note here can be taken literally, all right? So this is what? The total number of bytes held, expressed in BLS units, which is 1 kilo for the 8-inch floppy, not counting the reserved tracks. All right? So we need to do our math the same way and not count our 16K bytes worth of reserved tracks at the beginning of the SD card. If we put a number that's too big in there, then what will happen is CPM might try to store stuff in non-existent blocks, and we'd have a problem that will actually end up corrupting our file system, okay? So if you're going to do anything, make sure that this DSM number is rounded down, okay? It's okay if it's too small, but do not make it too big. All right, so down below our little save areas we looked at last time, I started putting some doc in down here. So let's document everything we just discussed, all right? And I've noted which things are required because CPM mandates that this is true, and which things are our choice, okay? So, start with our goal. What are we trying to accomplish? We want to be able to put a CPM-compatible file system on our SDHC card. And our SDHC card has 512-byte SD card blocks. And we need to be able to massage that in some way that allows us to put CPM sectors that are 128 bytes each onto our SD card. So I'm going to put 4 128 CPM sectors in each one of the 512-byte SDHC blocks on our card. And then we're going to treat each block as a track. And we'll see this will simplify our code. Think about it. Remember, CPM tells us what track in what sector number that we're supposed to transfer data into, do a read or a write. That's the information that it hands us on a silver platter. Well, if we massage this so that the track number is always going to simply equal the SD card block number, or more accurately, the relative block number, right? The offset into our partition, like we see up here in hex, the directory would start with SD card block number 20. And if we have 512 entries in here, it'll consume 16K, which coincidentally is the same amount of data that you remember the flash boot logic uses to read in its boot image, which has our operating system stuff in it, right? And if that is 20 blocks, another 20 blocks would be the size of the directory. Just a coincidence, all right? I'm just saying, all right? So these numbers here represent then the SD card block numbers relative to the beginning of this partition, which currently starts at 800 in hex. So anytime CPM comes along and says, hey, I want to read a sector, a CPM sector, starting on track number 20, we know exactly which SD card block has that data in it. We simply add this number here, which is the beginning of our partition within which our disk image is stored, to the track number that CPM is going to give us, and that equals the actual physical SD card block number that we need to use that has the data that they're looking for. So this is just going to be nice and convenient for us. All right, that's what I'm going with here. All right, now, these are the facts. CPM requires us to transfer data into and out of our disk in 128-byte sectors, and that's mandated. In newer versions of CPM, they allow you to do other things, but in 2.2, which is like the most widely distributed released version that ever existed, certainly in 1981, this is true, it required all these sectors to be 128 bytes in size. Now, keep in mind that we only have 64K to deal with, and you already now know that the 0 page has a permanently reserved buffer in it that holds one sector of data. And now you also know there's a second disk sector buffer somewhere, right? That's the one that we have to reserve so that the BDOS can do its directory operations in it. So that's 2 sector buffers, 100% dedicated to store data for CPM. And when the sector is set to 128 bytes, and you paying on the order of $250 for 4K of RAM, you have just shelled out about $16 for the amount of memory only to hold those 2 buffers that can't be used for anything else in the entire system. Okay? If you make this number bigger, you're dedicating more and more and more of your oh so precious and outrageously expensive memory to hold those bigger sectors. All right. So this was a wise choice back in the day. All right. Keep your costs down. Don't waste your resources. Okay. So what does all the other stuff then mean as a result of these assumptions up here? Well, number one, that means we have to have 4 sectors per track in terms of CPM lingo, okay? And this is because I decided to do this up here. What else is true? It turns out this is not really documented anywhere. I've never seen this in print. Somebody, put it in the comments below. Where is this defined? It must be defined somewhere because 8 megabyte limit is true in CPM. This is well known, but no one ever says why. I believe the reason is because this is the total number of values, right? 0 to 65535 is 65536 total number of values you can store in a 16-bit integer. Okay, so internal to CPM, internal to the BDOS, I suspect that what it does is it does all of its math in terms of sectors. And it needs to hold the sector number in a 16-bit register pair, and I'm sure that's what's going on here, okay? But again, I've never seen it documented that is the case. However, all the math fits, and that is the most likely reason why this is true. Okay, so if it can have this many sectors, which is, it is a CPM limit, I just don't know why, then therefore, this number of sectors times the sector size equals this many total bytes on the largest possible disk image, okay? Again, due to the way CPM is designed. So what does that then mean? We know we have 4 sectors per track. Therefore, this total number of sectors divided by 4 equals our system will have this 16K total tracks. Okay? Now, I chose the 2048 byte allocation size arbitrarily, but I explained why. Okay, it turns out this will be simpler for our first draft. Then what do we know? We know then that the whole disk has this many total bytes, and we divide it by our block size. We know that we have this many total allocation blocks on the whole disk. Okay. We also know what? I've arbitrarily chose that I want to have 512 directory entries. And that's my prerogative, okay? And if each directory entry needs 32 bytes, this times 32 equals this many total bytes for the directory. And with a 2K byte allocation size, I need to have 8 allocation blocks to hold our directory. Now here's the tables that I merged into one big table, and this giant arrow indicates that's the row you care about. So using all the stuff that we just went through in the alteration guide, here's our header, our one and only header for our one and only drive. We're not using sector translation, so that first word is 0. These other 3 words here are 0, simply because that's what they said to put in there. We then have to have a pointer to our directory buffer and a pointer to our DPB for our drive A. Remember our CSV, we're not going to do this. We're not going to use the checksum thing. So that'll be a 0. And our ALV is going to be a work scratch area that we have to allocate. So there's our CSV null pointer. And here's a label that we're going to put on our scratch area for our allocation vector scratch area. All right. Here's our one and only directory buffer that this points to. I'm going to just stick it right here for the lack of anywhere else to put it. Here's our DPBA. This is our parameter block for our one and only drive. Now, I remember what each of these are. There's quite a few. I probably should have done the same thing here. I'll do that before I push this up, okay? So what do we got going on here? We have 4 sectors per track. Our BSH, BLM, and EXM, we have to now look up in the table. Now, I say that's going to be 415 and 0. Let's look at our table up here. We know what? We know our block size is this. Our BSH, we look it up. It's 4, so I put the 4 in there. I know this is 15. Why? Because it says just look it up and stick it in there. And then we use 0 for this one. And the reason we put 0 in for this one is because the DSM, which is this the maximum block number, we have like 4K of these things. It's definitely bigger than 255, therefore this value is supposed to be 0. And that is the EXM value, right? Because of the math that we just did, and I knew, I wanted to double check what I put in here to make sure I'm right. This is wrong, okay? Our maximum allocation block number, when I did this, I put in the number that is the maximum block number if the disk had no reserved tracks. So this one, as written right now, is 32 too big. So I need to subtract 32 from that, which is going to be 63, not 95, right? Because why? We have a total of 4096 total allocation blocks. Therefore, if we use the whole 8 meg, the last allocation block number would be 4095. We're reserving this many, so we back that off, and we end up with 4063. That's what should be in there. Just once, I'd like to make it through one of these without completely screwing it up. The DSM is not off by 32 tracks. It's off by 8 allocation blocks. I'll make the change before I push up the code. What's our DRM? This is the directory entry number, okay? So that is going to be, it'll say down here, it's 1 less than the total number of directory entries, all right? So I said I want a total of 512. Therefore, my DRM here should be 511, okay? Now, we did the math earlier. We know that we need 8 allocation blocks to hold our directory total, okay? Therefore, the AL0 and the AL1 values, and these are 8-bit values, okay? We need to have 8 binary 1s followed by 8 binary 0s, because that matches this stuff in here, okay? If you're not following, pause it, go back and reread this, and make sure that this makes sense. You never know, I could have made another mistake. All right, so we need 8 ones followed by our 8 zeros. CKS is, remember, the number of bytes. It's the size of the checksum scratch area that we did not allocate up here. Therefore, the size is 0. And we already know that we have 32 in decimal reserve tracks. Okay? Now, to define the allocation vector, how many bytes do we need for that? Well, this number here just changed, and therefore I got to change it down here as well. I probably should have put this in a pound define. I hang my head in shame for defining all these like this. And equate. I meant to say equate. If it was C, I'd use a pound define, maybe. But in here, yeah, these probably should have been symbols that have equates on them, right? Remember the size of the allocation vector. It's DSM over 8 plus 1. And because our DSM here is 4063, that's what I put down there. All right. This number is always odd because this is always one less, whatever. On our system, it will be. I suppose you could have a disk that has a wonky block number for the last one that is a multiple of 8 or whatever, and then this would come out weird. But I'm okay with this. I know this is not a multiple of 8, otherwise we could fix this, right? Worst case scenario is you waste 1 extra byte using this math the way they've expressed it. Okay, now what do? We got all this defined. Hopefully it's right. We now have something we can return in our select disk function up here. All right. Now, remember before, what I did is I stored it, I printed it out, and loaded HL was 0, and I returned. Now, as I discussed earlier, they have an example code that does all the math and stuff like this. If you have multiple drives, and is the drive that are these the droids you're looking for? If no, return an error and stuff like that, right? So we don't need to do all that. We only have one and only one drive. So look what I've done here. Save it. And we need to ask ourselves, is this wise? All right. This kind of goes to that thing in the 0 page that holds that current disk number. I mean, think about it for a minute. If you are asked to select drive B, we only have one disk. We only have a drive A. Should we really store drive B, which is the number 1, in our local value here? Or should we first check it and not then risk storing an illegal disk number in our storage area here? Okay? It's not really clear what we should do here. Now, I do initialize the drives down here, as we saw earlier, to very illegal values for debugging purposes. So, if these are incorrect, it turns out they're incorrect when we boot up anyway, for debugging reasons, okay? This may come back to haunt us, is my point, if we just blindly store it like this, all right? So that's why I got a little comment over here. And we'll deal with this later on. We'll do a bunch of tests and find out if it's okay or not okay to just store garbage in our local working variables, risking a potential problem later on. We'll probably have to just validate it later on during the read and write routines and stuff like that, if we are going to allow illegal values to be put in there in this code up here. It just has to agree with the rest of the code. That's all I'm saying, all right? So we're going to store it no matter what. We're going to dump it out. The reason I want to store it, actually, is because, remember, the debug disk routine is going to print it out from its stored location. So for now, our first release, that's what I'm going to do. Now, down here, this is similar to the code they give us. I'm going to set HL to 0, because if I ask, is the disk that they want 0 or not? Okay, this is how you can ask that question. Remember, this is going to clobber the C register. It'll also clobber the accumulator when it runs. So I need to save it somewhere so I can get it back down here, and then ask, if I OR A with itself and the 0 flag is set, then I know A was set to 0. All right, this is more efficient than saying compare to immediate, a 0 byte. A C compare accumulator to 0 is a 2-byte instruction, but OR A with itself is only a 1-byte instruction. So these are the techniques you pick up, all right? So this is asking, is the disk that has been requested in the C register up here, stored in there, and then reloaded, is that equal to 0 or not? If it is, we're good. If it's not, the 0 flag is off. We return non-zero, HL is set to 0, and that's what we did last time, and it says, hey, the disk is invalid. But if A is equal to 0, we fall down here, we put the DPH address in the HL register, and bang, we have now told CPM that the drive is valid, and it has the disk parameter header that it needs so that it can, set the track numbers and sector numbers and start trying to do I/O. Now, with the code in this state, let's compile it. Learn how to type and program it onto our SD card and boot it up and see what happens. Fingers crossed. Now look what happens. It no longer says bad disk, it says bad sector, and we've got further. So let's see what happens here. Now remember last time I said I would set the DMA in my warm boot before I moved on to the CCP, so that line of code was added up there, right? Here's my 0-page debug dump. I'm on debug level 3, so it's really noisy right now, and that's fine. So what happens here? Here's the set DMA that the CCP does to set it to 80, which is already there. It doesn't matter. Then it says, I want to select drive A. And this is where it crapped out last time because we said drive A was illegal. Now we gave it a DPH that makes sense. So it says, okay, thank you. I want you to move the head of the disk over to the home position, which is to track 0. And remember that code fell down into the set track routine and said, I want to move to track 0. So that's why this thing changes from garbage to 0 at that time. Okay. After that, it says, I want to set the track to 20. Remember, that's an interesting number because 20 is the first track, as far as CPM is concerned, of data that holds our directory. So what it's probably getting ready to do is read the directory to build that allocation table thing, right? So now what does it do? It sets the sector to 0. And that makes sense. That's the first sector on the first track that holds the directory data. What does it do then? It says set DMA to EE0F, whatever the heck that is, right? Then it says I want to read data from the disk, and that makes sense. It's on disk 0, which is A, track 20, which is the first track with the directory stuff in it, sector 0, and EE0F. Okay, let's look at our listing file here and see what EE0F really is. That's our directory buffer right there. Okay? This is retro.lst, if you didn't catch the typing there, which is the output of the assembler, right? Which tells you, where everything is. It gives you all the, addresses and the bytes that are put into the binary file, okay? So that's exactly what this thing is trying to do right now. If we had a file system and we had the read routine implemented, we'd be running. Now, I'm going into overtime again. What else is new, right? Let's look at one little thing we can do here, which I think is worth the extra time today. If you look at my read routine up here, what I've done is I've added some code in here. All right. This is what we had last time. And I have an if in here so I can comment out this. You've had an error while reading, and I've replaced it with this. Look what this does. I'm going to do my little LTIR game. I'm sending every byte equal to E5 in the 128 buffer that's been pointed to and set earlier with the set DMA routine. E5 is a magic value that IBM decided to put into every byte of every sector on a newly blank formatted floppy disk. So if by doing this, what I'm really doing is I'm telling CPM that the disk is blank. This is a brand new disk, a virgin disk from IBM, just put in there the first time. Now, this is fine and dandy, provided that nobody tries to actually read the operating system tracks, right? Because it'll also be set to E5, which is not supposed to be what those are, all right? Now, it turns out, as the documentation said, we saw it before, that the track offset number will always be added to every call before it does a call to set track. Okay, which tells us that CPM will never try to read from the reserve tracks. All right, so this is safe to do. So we're mocking a brand new blank floppy disk. Let's compile and run this. Let's see what happens this time. Fingers crossed once again. Now what is it doing? Hopefully it's not stuck in an endless loop. Look what's happening in this column right here. This is the track number. It's counting 25, 26, 27, 28, 29, to A, to B, to C, and so on. It's reading all these tracks. Remember, our directory started on, from CPM's perspective, on track 20 in hex, and it ends on track 3F in hex. It's reading every sector in order of the entire directory. 39, 3A, 3B, and so on. Hopefully it'll stop in here. Hopefully I didn't write an endless loop. Ah, perfect! And we have the A prompt. We have booted CPM with a blank disk. We should actually be able to do a directory command right now. Now it's going to poke around and look at the directory some more. Not sure why, after it just read the entire thing. And when it built this allocation vector, I mean, if you think about what that really means, what it probably did is it optimized some other stuff, you know, all those reserved, you know, scratch areas and things like that that are in those various fields. It probably keeps track somewhere of how many files there are that it saw when it was doing all this up here and stuff like that, so that it could optimize the number of accesses back to the disk if I ask it to print out the contents of the directory, right? So, in other words, it doesn't have to read the entire thing again. That's just going to be operating system, optimization stuff that is, you know, behind the curtain, as it were. You can reverse engineer the source to figure out how it all works, but basically, I would argue this is a pretty nice feature if it optimized it down to that. So we have booted CPM. I feel like I need a sound effects disc or something. Woo-hoo-hoo-hoo! Or trumpets should be blaring here. Anyway, thanks for watching. I'll see you next time.